starting with equations of lines where we want to find an equation of a line given some information. We have two different formulas that we use for this, the slope-intercept form and the point-slope form. They have some things in common. One of those things is that they both have m, which is the slope. So m has the same meaning in both formulas. For the other constants, they differ. The slope-intercept form has this b here, which is the y-intercept of the line. The y-intercept is specifically the point at which the graph crosses the y-axis. So it has x-coordinate 0. So this is really the point 0, comma b. In the other equation, we have coordinates x1, y1, which could represent any point on the line. So it doesn't have to specifically be the y-intercept in this case. It can be any point on the line. So we need two coordinates because there isn't one that's implied to be 0. So which of these we use just depends on what information we have. If we happen to know the y-intercept, we use the first equation. If we don't know the y-intercept, if we're given maybe another point on the line but we don't know the y-intercept, then we use the second equation. So one such situation that can come up is a graph. If we're given a graph of a line and asked to find an equation for it, we usually start by finding the slope. So to find the slope, we can choose any 2 points on the line that we can read clearly. We don't want to have to estimate the points, so I'm not going to choose something like this one here where I would have to estimate about where it is. The two that I picked happen to be intercepts, x and y intercepts, but I could just as easily have picked this point down here because I can read it clearly. That appears to be at 4, -15. So any 2 points that you can read clearly are fine, and then draw in a right triangle. And based on that right triangle, count a rise and run to figure out your slope. In this case, we can tell that that slope is negative. I don't really recommend trying to think of the rise and run independently as being positive or negative. Instead, just look at the whole line from a distance and say, is that line increasing or decreasing as you read it from left to right? That way we can count our rise and run as unsigned quantities. So I can tell this is negative, so I'm going to put a negative and then get ready to create a fraction. For the rise, I don't just count that it's 3 squares. I also have to look at the scale on the y-axis. Each square is worth 5 units, so that total rise is equal to 15. Same thing going on with my run. It's only 1 square, but each square is worth 2 units, so my run is a total of 2. And that gives me a slope of negative rise over run 15/2. In this case, I can also see the y-intercept because I have a graph and I do have the part of the graph that crosses the y-axis. So if it's really easy to find that y-intercept, we go ahead and just say b is equal to 15 and go straight to our equation. Y equals m, which is -15/2, times x plus b, which in this case is 15. Another situation in which we might want to find a linear equation is when we're given a word problem that has perhaps a point on the line or a starting value and a rate of change. We are asked for a function v. This is going to be a linear function. We can tell that it's linear due to the fact that this description says it decreases in value at a rate of $300 per year. Because that is a constant rate of change, we know that this is a linear function. So if we're asked to find a linear function, that's really the same thing as finding a linear equation. We just need to make sure that at the very end, our final answer is expressed in function language. So what we're going to do here is identify the pieces that we have. Right? If this function decreases in value at a rate of $300 per year, then that tells us what our slope is. Decreases suggests that the slope is negative, and $300 per year, it's fine to use negative 300 as long as we assume that our x units are years and our y units are dollars. We're also told that this computer is valued at $1,800 initially. That initial value, that's when we're starting out, right? If x is the number of years after it's purchased, this is when x equals 0. Which tells us that what we're really given here is the y-intercept. So the b is equal to 1,800. And therefore, using our y equals mx plus b model, we get, instead of y, we're going to call this v. We're told to call the function v, so let's call it v of x, since x is the input variable. The slope is negative 300 times x, and the y-intercept is 1,800. Now, of course, this model doesn't apply for all real number values of x. So when we're asked what is an appropriate domain for v, we're really asked what x values can we plug into this and get a reasonable answer that actually applies to this model. So for starters, we can see that x must be at least 0, right? We're not interested in backing up and trying to predict what this computer was worth before it was even purchased, right? Or before it was even built, right? So we're figuring x equals 0, that means it's brand new. The model doesn't really apply for negative values of x. It's also going to stop applying once the value of the computer gets down to 0. If you end up with a computer that's worth negative $10,000, well, that's great. Or not if you own it, I guess, but if you want a computer that's worth negative $10,000, that means you get the computer and you get $10,000. And well, that just doesn't happen very often. So we figure this also stops when v of x is equal to 0, since this is a decreasing function. So that's why we want to find out what value of x that corresponds to figure out the end of our domain. If we set our formula for v of x equal to 0, it gives us an equation that we can solve, and it'll be a little bit easier to add 300x to both sides just to get that positive than it would be to subtract 1,800, but it doesn't really matter. Either approach will work. We get 1,800 equals 300x. Dividing both sides by 300 gets us 6. So after 6 years, the computer is worth $0. It's reasonable to guess that an appropriate domain is from 0 to 6 years. So we had to do a little bit of algebra and a little bit of thinking about the context of the application in this case.